We're still a few short, aren't we? We'll start and then. So what do you have to do? Do you have to show that you've attended that? Things have changed. Okay, has anybody got any questions from yesterday? No? Well, yesterday was sort of an easy introduction. So today it's the heavy stuff. So try and bring it into perspective for you. So you got no questions from yesterday? Morning. So why else would I need to know the temperature at the inlet and outlet of the plant? Can you give me one reason why I want to know the temperature? We talked about what? Cool down. So what does temperature affect in a fluid?
The phase?
Fizz?
Yeah.
You mean the viscosity?
Phase of the change.
Oh, the phase, yeah, yeah. But normally it will change the viscosity. If you've got a pot of treacle and you warm it up, or a pot of oil and you warm it up, it'll pour out much more quickly. So we need to know the viscosity. So we need the temperature to work the flow, and we need to look at, as we did yesterday, look at the cool down, make sure that it doesn't cool down such that we get wax formation or hydrates. But from a structural point of view, we need to know that temperature profile so we can do structural design. So what the first thing we've got to do is pipelines expand at their ends. And so therefore, which end would you expect to expand the most? The inlet or the outlet? Inlet. Why? Because it's hotter. Yeah. Yeah. So we need to know that. So that and the cool down we talked about yesterday. So now we're going to go into looking at how you design the pipeline structurally. And for that you need to look at all the loading effects. So what do you think are the main drivers that affect the pipeline? Where do the forces come from? Thermal, it comes from temperature and pressure, and then the other thing is they come from gravity, because it's a mass and it will deform. So the combined loading, internal pressure, function of the well air pressure and pump pressure. So if you're pumping from one place to another, then the pressure in the line at the inlet is a function of how hard you pump, the pressure of your pump. External pressure is the water pressure. Good morning. Is the external pressure plus the atmospheric. Changes along the length. So if a pipeline starts off in 500 metres of water and finishes off at 200 metres of water, then there's an elevation change. So the external pressure is different at the outlet as it is at the inlet. If it's going deeper, then the external pressure is smaller at the inlet than it is at the outlet. So that is a function of how much the water depth, and we talked about the water pressure being the column of water acting on the pipe. Axial forces, we're going to go in more now to look at the effects of both pressure and temperature on axial forces. So it changes due to variations in operating temperature and differential pressures and the end effects. So all those things we've been talking about. And then bending. We design the pipeline for its, what we call it, its in place design. We've got to get it there, so we design it for, it's got to make sure it's going to get there without being damaged, in other words being overstressed. Or so once it's on the seabed, it's got to perform its duty. Local variations in bathymetry, because seabeds are not straight, they're not flat, they undulate, yeah. So who knows what, everybody knows what a hoop stress is, do you? Please nobody say no. Right, so you can tell me then, can't you?
Circumferential stress.
Yes. Why we don't call it circumferential stress, because so you know what that is, so I needn't dwell on it, but this is a horrible door and I keep meaning to change it. So do you know how it's derived? So oh good, so I need so it's the pressure acting on that internal surface. It's acting up, and the external pressure times that surface area acting down is the difference between internal and external pressures. And the stress is trying to pull these two apart, and the stress is carried by that plus that. In other words, this area times 2. We're all right on that. Does anybody not understand that? Because it's important that you do understand it. Okay, so we're all right to move on from that. Good. So if we take that, then we can work out the hoop stress is PI is your internal pressure times your internal diameter, which gives you that force in that direction. External pressure times that diameter, because you're looking down on it. So that is the difference in the force divided by twice the thickness. But there's no length, so because it's per unit length, so length is 1. So that's the hoop stress. Who was the famous engineer that came up with that? It was a gentleman by the name of Barlow. Barlow's theory. If you've not got any external pressure, that can be reduced to PD over 2T, which is the standard pressure in a pipe in air. And so it's Barlow's formula. So you can change it to PI minus PO. So P internal, PO is external, times the diameter. Now, what D is that? Is that the internal diameter? The external diameter?
The outer diameter.
Why?
We assume it's
There is no reason for it. We just assume it. So, but we're going to change things. Some people use the DI, some people use the outside diameter. More often than not, we nearly always use the outside. But then, there's another way of doing it. You can take the mean diameter. So how do I get the mean diameter, girls? Come on.
And it's an approach external diameter.
The mean diameter is the external diameter plus the internal diameter divided by 2. So that's the mean diameter. In other words, it's the mean diameter. It's that it's a diameter in there somewhere, which is D outside plus D inside over 2. It's just another way of doing it. I would just assume you are absolutely right as usual, and I would just stick with the outside diameter. Okay. But some codes don't stick with the outside diameter. They change it to sometimes they use a nominal diameter. And we said yesterday that a pipe can have a 6-inch pipe can have an outside diameter of 6.625, but then they'll use the nominal diameter. Mean diameter version. So you put D, the Hooke's test, we're using dm minus T over 2T. So that's a mean diameter version of it. Where dm is, we've just said an Linda written it down. Now, if you take them all, all the ballers for all the methods of using it, whether you use the one we've got on the left, which is the ballers form, but use the DI, or you do it as this is shown, where you are actually working out PI times DI, PO times DO over 2T. What you find that Barlow's formula, which is the top one, will always give you the highest stress. So that's the most conservative design. You want a pressure that predicts the highest stress, and you never go above that stress. So the hook and radial stress varies through the wall thickness. Anybody know what Lamé's theory is? Lamé's theory? No? Well, as we said, pressures are getting higher. So what's going to get higher as well?
Stresses?
Stresses, to keep the stresses the same, if the pressure's higher, what you've got to do?
Increase the wall thickness.
Spot on, yeah. So but normally we call that is a parameter you'll know and know a lot of. Yeah, get to know that, the D over T ratio. You'll see it in a little while. It's a non-dimensional parameter that we use a lot for collapse and buckling. We use it a lot for the thermal analysis. D over T. If that is greater than or equal to 20, and that is thin wall. If it's less than 20, that means it's a thick wall. So that means so in that respect, the thick wall, like here, if this is drawn thick, the hook stress will vary from inside to outside. What you've done in the other Barlow formula with the thin, you've assumed that the hook stress is constant straight through the section. With thick wall, it varies throughout the section. It's greater on the outside than it does on the inside. So to do that, Lamé produced a theory which I can show it you graphically, but you don't really need to worry about it. But that's the formula for it. So, as often in design houses, they won't bother with the morning. They won't bother with the normal Barlow's thin wall theory. We'll just use thick theory, because that will give you the actual stress. Morning.
Good morning.
We're building up. It's getting a bit full now. Any seats left? Right. So some people just never use anything else but this thick cylinder theory, because that's actual stresses. So your actual hoop stress maximum is given by that. So that's thick cylinder theory. So a typical allowable stress expression for wall thickness is that. So now you can see that's Barlow's formula, where this is outside diameter, if that's what you want to do, most likely. Because if you take that as the outside, that's giving you a bit thicker. If you use a smaller diameter, thickness is going to be smaller. So use D and you can't get any bigger than that. But there are two things in here, and this is out of the typical API codes. Y is the yield stress. F1 is a design factor on yield. And F2 is a manufacturing tolerance. So, somebody speak.
Yeah, it's just question regarding this manufacturer tolerance. Are you going to explain this?
It just comes out of the code book. It gives you figures that you use. It's just a safety factor, allowing for manufacturing defects, allowing for changes in material properties. Yeah. If I asked you to draw me a stress strain curve for a steel, what would it look like?
Engineering stress strain or true stress strain?
Stress strain. Would it be like that?
No.
Oh,
It's a weak
it's a
material.
plastic region.
So would it be like that?
All the skills got shoulder,
Yes.
Is that what you understand as a stress strain curve?
The older ones are trying to get rid of the shoulder and make it smooth and have the skills.
Why is that? How do we do that?
Let's work out that a bit.
Steering technique.
There's two famous guys, both work. One named Ramsgood, Ramsberg and Osgood. If you take a pipe, manufacture a pipe, and you want to get the stress strain characteristics, what they normally do is cut samples out. You give the drawing. So we try to put that in somewhere in the middle. Also, the pipeline has a longitudinal axis. So we also cut stresses out, test pieces out in that direction. Oops. We cut them out in that direction, but they're still in the centre of the steel. Now, if this is really thick wall pipe, that stress strain curve of those is more appropriate to that. If the pipe is thin wall made out of plate, then this changes. And you get a series of them. And these are what are called modified stress strain curves. So that your shoulders disappeared. So external pressure. Okay, let's look at external pressure. Just wonder if it's jumping a little bit. If I've got a pipeline and I've got external pressure, theoretically, being the pressure on the top of the pipeline is slightly less than the pressure at the bottom, but we take the pressure being the bottom because that's means, but it's so different, so small, it doesn't make any difference. But that pressure acts all the way around. So what kind of stress is that going to put on? Perfectly round. This pressure is equal. This is a perfectly round cylinder, and that pressure is equal all the way around. You just told me if I put pressure inside the pipe, it wants to expand and give me a hoop stress. So what's this stress going to give me?
Compressive stress.
In what kind?
So the hydrostatic stress?
It's going to give me a compressive hoop stress. So in other words, the element there will go into compression. Yeah?
So, which one is radial stress?
Radial stress, that's the one that way. Yeah? So the external pressure is going to give me a compressive hoop, and the internal pressure is going to give me a tensile hoop. So if I've now got the pressure inside and outside, I've got to take that pressure inside from the outside, find the difference, and that will give me my resulting hoop stress. And if this pressure inside is higher than this, I'll always get a tensile hoop. So what I'm doing is looking at, I think in fact there might be, can you just look at it? Just check, going back a little bit, just for your interest. This stress in that direction from here is in the hoop, and this is in the longitudinal. If you manufacture a piece of pipe and cut all these test pieces out, which would you expect to give you the highest stress strain curve? That one or that one?
The good stress.
No.
Yes, good direction.
You think that one, or this way,
The one you just wrote.
Why?
The budget.
Why?
Because of the orientation of the rolling grains
Yeah.
in the manufacturing process.
So okay, so as long as you appreciate it. And then sometimes there is you have to satisfy a relationship between ratio of those when you buy the steel. So let's go back to the external pressure. So we now, in a perfect round pipe, it will produce you if there's no pressure, when I lay the pipe, if I can get this down on the seabed, and there's no pressure on the inside of it, or what happens when we lay in the pipe, before it's coming down off the lay bars, we put a cap on it. So we've locked in the air, and that is atmospheric pressure, except for the weight of air down the pipe to the seabed. So it's effectively nothing. But when we lay that on the seabed, it's now effectively straight. We've got the external water pressure plus the atmospheric pressure, and atmospheric pressure on the inside. So that's going to give me my maximum compressive hoop. So when I now put pressure inside, that's going to expand. So it's going to expand it, but it's first got to go expand it and take it back and overcome that compressive stress, and then put what's left into the pipe. So right. Don't worry, you got the right day. Don't worry. Right. So we now know that when we have a perfectly round pipe, but if when we lay it on the seabed, I put this pressure to be so very high, has anybody got a plastic ruler? Yeah. Now, is it insured? Right. Good, you're arguing. I'll always like to see it when you're arguing. You all know that if I've got that ruler or a beam and I press it, at some point it'll deform, bend. So, but I'm putting a force that way and a force that way. I'm not putting any force that way. So what's it doing? It's called buckling. Buckling. And there's a very famous other British scientist called Euler, E-U-L-E-R. So, but Euler also, I'm afraid of this, is this better than mine? Shatter resist, top quality. So if you do that, so he also developed a lot of theory as if his loads weren't like that. I've just done that, and I put a force on there, but I put it on my two hands flat. He also did it for when it was pinned. And he also, well, I must do it this way now, but he also did it when this was offset, eccentric, a bit like me. Right. So, if I now are you sure it's not insured? If I now take that, and I've already got it bent, and I push it, I just bend it even more. So, there will become a pressure in here and I'll draw it thin wall. I think I've had too much to drink last night. Right, if that pressure's on there, if this stress comes to a certain point, this is all in compression because we've got external pressure. The wall of that pipe will want to buckle, just like this. Okay? Just buckles. So then it goes out of shape. And it buckles in a certain way. And as we'll see, it always buckles in what we call the peanut shape. And you'll see why. But we did say that your stress strain curve, oops, wrong one. Normally if it goes plastic, then fails. But this can buckle and go out of shape before it even goes out of elastic. It doesn't have to go beyond into the plastic range. It can actually buckle when the stresses are in the elastic range. And it's called elastic instability. So it does undergo elastic buckling. So, if we've now got a nice round pipe, the pressure on it, and I've drawn it with a nice uniform wall thickness. So if that pipe is basically eccentric, the bore is not concentric with the outside, or that wall thickness varies from around the pipe, then that will be different. But this theory is assumed that pipe is perfectly round and of uniform wall thickness all the way around. So we've just said we'll get a hoop stress, and that hoop stress is, what is it, compressive or tensile? Compressive. Oh. So the elastic collapse occurs due to external pressure, and it goes like that. It doesn't necessarily fail like this, because normally if it's a big pipe, it's sitting on the seabed, it's been gone out of round anyway. So, which we'll talk about in a minute, but this is theoretical. So it'll go into this peanut shape, and you can see why they call it the peanut shape. So we now can establish an elastic critical buckling pressure. In other words, if I take a theoretical perfectly round pipe, then I can establish the critical pressure, elastic critical pressure, that it will collapse or buckle, and that is a function of transposing that. So here you see 2e T over d raised to the power of 3 over 1 minus. Does everybody know what this last sign is here? Absolutely, right. So it's Poisson's ratio, as long as you know that. So, but you can see this. That is a function of the material properties, elastic modulus, which is the slope of that line. That is the ratio, Poisson's ratio, and then this is characteristic of your dimensions of your cylinder. So this is a pressure. That cylinder will collapse where that's constant, and if so, therefore, for knowing that, you can work out your critical pressure. So E is the elastic modulus, R is the radius of the pipe, T is your wall thickness. Now that radius of the pipe is this radius from there to there, half your diameter. Poisson's ratio. So that is a perfectly round pipe, and it's the critical pressure. So that's the pressure. If it's perfect, it's going to collapse off, but nothing's ever perfect. So the actual buckling pressure is less because of initial ovality. We manufacture it oval, and we put it on the seabed and we bend it. It goes oval slightly. So you've now got buckling less because of initial ovality and plasticity effects. Typical sinusoidal imperfection. So if I start off with a round one, and this is the way it's done for convenience, perfectly round, and it goes elliptical. So under external pressure, initial ovality increases until the combination of bending stress and compressive hoop stress induced in the pipe reaches or causes collapse. So if you look at that outer roundness, we draw it again. Draw it the other way this time. So if we take the diameter of the blue minus the minor axis of the red ellipse and divide it by 2, then you get delta D over 2. And then you do it the other way, delta D over 2, So, well, let's go back. So, taking account of the initial overhauling, the pressure at which the yielding and hence collapse occurs can be determined by the following quadratic. So you've got quadratic. So anybody recognise the quadratic equation? That has a quadratic equation. If I wrote on here, ax squared equals bx plus c, you'd know it as a quadratic. And that's how it's solved. Where PP is the minimum yield stress times 2T over D, and SMY is the safe minimum yield, D is the outside diameter, and T is the wall thickness. And FO is given, if we have a pipe, we measure its smallest diameter, add it to its maximum diameter, divide by 2. Divide by the diameter, and that is its mean diameter. So we come up with this FO, which is initial unloaded ovality, as manufactured. But it's not just manufactured, it's when it's sitting on the seabed. Let's go back. So you've now got a pressure at which the pipe will collapse when it's perfectly round and subject to a perfect uniform pressure around it, and that's the critical pressure. Then, because we've got imperfection, we've got out of roundness, we can now change that and come up using this formula to come out with a pressure that which it collapses at due to a more realistic figure. So that's just due to pressure. I'll better give it to you back. You'll have to imagine I've got a piece of pipe. And I bend it. Anybody does any plumbing? Not these days. You take a piece of pipe and I bend it. Now normally I'm going to take a piece of pipe which is originally straight, and I'm going to bend it like that. To bend it, I'm going to put moments on it, there and there, to bend it. If I take a piece of pipe and bend it, then what am I going to get? I'm going to get, what's the stress am I going to get at the top here? Tensile. In which direction? Right. So if I look on the top, so that's my stress in that direction, longitude. So what do I get underneath? Right. So I've now got tensile there, and I've got compression there. So these are longitudinal stresses, sigma L. So therefore at the top it's tensile, and at the bottom compressive, negative. So we're always going to have two values for that bend stress. Compressive and a tensile. Okay? And we'll always assume, we'll point to this, but if anybody's doing some big pipelines like water mains and things like that, where they put a concrete jacket around it, then the concrete jacket, but what's this point here called? If I do that, it's going to bend about that. So what's the stress going to be at that point? Zero. So okay. So that's X. We call that XX, and that's called the something axis. It's a good education. Benefits of a good education. Right. Neutral axis. So now, if you start putting a big concrete jacket around it with reinforcing bars in it, concrete doesn't like going in tensile, but it only loves compression. So what happens is the concrete will crack unless you've got the reinforcing bars in it. So you can then work out, but you will actually get a shift to this axis downwards if you bended it. So that's the concrete around the outside. And this is reinforcing bars. What they'll do is they'll ignore the tensile, say that's got no strength whatsoever, and we'll work out the shift in this neutral axis. So this is compression, compressive side, and this now will move down here. So what's going to happen to this fella is going to be like that, through the pipe, and there's the concrete coating. Your neutral axis has come down here. So now it's through that. So I've got a smaller compression stress and a larger tensile stress in the pipe. So we don't normally put concrete on. When we put concrete on, to weight pipes down, we don't consider its strength at all, so we just ignore it. But for those big pipelines, there's a very big one that I was involved in down in Brazil, and I could walk inside it. It was bigger than me, and it had concrete on it about that thick, and so that made a big difference to the structure. So if I took a piece of pipe like that and I started to find moments, what's going to happen to it? this part of it here, as we said, I've drawn it the other way up. This is going to go into compression here, and it's going to ruckle eventually. So there will come a pressure, there will become a bending moment that implies that where that compression becomes so great, it'll buckle just like the plastic rule buckles. And that's called critical bending moment. So now we've got two critical conditions, a critical pressure and a critical bending moment. That's what you can get with concrete, and this is this and the thing at the back here. This was a 36-inch down. It looks much bigger. We were quite relieved when we found the guy that painted those numbers on. We were actually having a coffee when he failed. He'd gone in. But what happened is this stinger was a buoyant stinger. It was filled with air. And it ruptured. Filled with water. And of course then it went like that, and the pipe got overbent, broke. So this was a bending failure, and collapse of the pipe. Once you've got a pipe collapsing on the seabed, it's a mess. It's a major problem to get it back up again, because you can't just go and grab it. So there are methods where you just go and you have to cut it off, put something inside it, inflate and pressurise it, grab it, and then bring it up again. But with difficulty. What time's your break this morning? 10:30?
Yeah.
So, if you do your stress strain curve and you look at your bending, in the yield stress, in the zone of the yields, then you can bend that and it stays round. When it starts to go round this part of the stress strain curve, it starts to go out of round, which is what you'd expect. If you get a plastic pipe and you can bend it, and you can see it, and it'll just crumple. Until you get to the end where it's virtually far end of your stress strain curve, it'll really go to buckle. So, but that's just due to bending. How do we get bending? Well, we get bending when we're laying, which we'll see in a little while, and that's the time when we've got to be careful. On steel risers, catenary risers, we've got depth pressure and we've got bending combined, so we have to, that's a live load. Normally when we're laying, you design your installation technique to make sure the stress, bend stress, or maximum stress during laying is no more than 80% of the yield. That's a normal, typical construction stress. So, what's that critical bending moment? Well, this is the formula for it. Now all this came out from a program which was carried out that I was involved with Shell in Houston, Texas. And it's when we first started going into deep water. But deep water then was nothing like what we call deep water now. So that is a formula, and again you can see you've got the same parameters. Wattle ratio. Hang on. That shouldn't be there. We've got E, elastic modulus, D is the diameter, T is the wall thickness, and Poisson's ratio. So that external pressure shouldn't be there. So you now end up with a critical bending moment. So if I take that pipe and bend it, there'll come a point when it collapses, just from pure bending. So now I've got a situation, well, when I'm laying a pipe, and this will be all together. I bend it there, which we'll see in a minute, and I bend it here. And then it goes on the cement. So the critical point when you're installing it is the combination of bending and external pressure at some point around here. So you've now got to combine effect of pressure and bending. So if we now plot bending moment against what is known as a bend strain, but this R is not the radius of part, this is the radius of curvature. Okay? So this is your bend strain. So if you plot bending moment against bend strain, you come around here until it comes to that where it'll buckle. That's your critical point, it'll just go bang. And these are produced by actual bend tests on it in a rig. But if you now change the D over T ratio and increase it, what you find is that the you get different points at which it will fail. In actual fact, what you can do is you can connect these all up with a nice straight line.
So, what is the structural difference between bending and buckling?
Bending and buckling, what the difference? Well, if you've got no pressure, you'll get pure bend, collapse due to bending. And if you've got pressure but no bending, you'll fail due to pure collapse. But that situation will never arise, because you'll always have, like here, when you're laying, you'll have pressure and you'll have bending. So you've got to be able to combine them. There's both loads. When you bend a pipe, take it down to seabed, it'll also have pressure on it on the outside. So it's subjected. Which would you expect to fail the sooner? A pipe that's straight with pressure on it on the outside, or a pipe that's been bent with no pressure, or one that's got pressure and bending on? The last one, yeah. So we'll show you how to combine them in a minute. If I now take the collapse, I can now take delta D over D, which is the change in diameter as it starts to deform, change in diameter over the bend strain. Then again I get external pressure, points at which it will collapse, So if I increase the external pressure, it collapse sooner, low bend strain. And again, you put a straight line through those. So, we've now got a bending moment. We've got a critical bending moment and a critical pressure, which are two failure modes. But we've actually got an actual pressure and an actual bending moment, M, and an actual pressure, P. So you use this formula to look at what is the safety, and you put a safety factor in, maybe 1.5, 2. So how do we combine the two? M is your allowable bending moment. So if I've got a pressure, water depth pressure, that's not going to change. The only thing that can change, if I'm going to lay it into that water depth, that pressure's there, I can't take it away. The only thing it can do is limit the amount of bending. So I've got a pressure, I've got a critical pressure which will collapse on its own without being bent. I've got a critical bending moment which will bend without a pressure, but I've got an actual pressure P from the water depth, so I now need to know what the allowable bending is to avoid collapse, and I put a safety factor of 1.52. So MCR is the critical bending moment, P is the external pressure, and PCR is the critical bending moment. And F is the safety factor. And therefore you can plot those. If you take that graph, that formula, and you start changing the values of P and M, so this is what's known as a failure ellipse. This is part ellipse. If I've got no pressure, pressure 0, yeah, then I can take M up to an equal MCR to get a figure of 1, and that'll be there without a safety factor. It won't fail. If I've got here 0 bending moment, I can increase its pressure to here, so P equals PCR before it will fail. So as long as I stay inside that ellipse, it won't fail, theoretically. So, but if you're now put in another line down here, and say I'm going to stay in that, that's the safety factor. Can I just pinch a look at you? So don't worry too much about this graph. If you take a pipe down to a certain depth and certain bending, there'll be a pressure at which it'll actually trigger or initiate the buckle. Now there's a very famous situation with a very famous oil company that nearly went bust. British oil company, BP. They laid a pipe, and it was one of the first pipes were laid in the North Sea, and the consultant, which wasn't me, went across to them and said, you do realise that if you bend that pipe, it'll go flat, not locally, but the whole length. Your pipe will go flat. So BP rubbish. So we're all summoned off one of the best holidays. We were in the Mediterranean, and we had 2 big lay barges end to end, and we had a long pipe, and we hung it on what we call davits. So it was a straight pipe, and then we lowered it down to the seabed all the way. But right in the middle of it, it had a crimping tool to put it, deform it. And what we were looking for was how far, once we'd initiate that buckle in the middle, how far it would travel. It went off with such an almighty bang, and both lay barges rocked over because we'd lost all the buoyancy from this pipe, which was about this diameter along its full length, which we were holding. As soon as it went like that, the whole 2 lay barges went like that, lunged over, because we lost. And the buckle, within milliseconds, it travelled to both ends, 200 metres, 300 metres away. So we realised then that once you initiate a buckle, it can propagate. But once you've initiated it, the pressure to make it propagate is much less than the pressure that initiates it. Because you've already, once you've initiated, it's already gone out to shape and out to round. So that pressure just acts on progressively all the way along, just to both ends. BP have had a number of really good situations where they've had people's, like for instance, there's a very big one of the first big jacket structures that were installed in the North Sea, and it was 125 metres tall, and somebody went to BP and said, how are you going to install it? Well, we're going to install it on a barge. We'll pull it onto a barge, and then we'll take it out shore, and then we'll ballast the barge and let it slide off. And it'll slide down to the seabed, and it'll go. It'll be upright. So it's the consultant. It won't. He'd worked it out, this thing would go over like that and just keep going. So the whole jacket would have been on its side on the seabed. So what we had to do was we had to put 2 massive spheres on the other side of the jacket with buoyancy controls in to compensate for this inertial effect of the jacket going over. And it didn't. It went over, and it was perfect when it was installed, but it would have gone over. So back to transgressing. Propagation. So all as this little chart does, it's not a very good one, is if you initiate a buckle in deep water, then that buckle will propagate until the energy from in the water no longer is capable of propagating that buckle, and that's the propagation depth. So once you've initiated the buckle, it will propagate. If it's in a depth below the propagation pressure, water depth, then it'll propagate till that water depth equals the propagation pressure, and then it'll stop. But it will run on a bit, but whereas we won't go into. So that's the propagation. So it's a form of buckling which travels and propagates along a pipeline. It does not initiate the failure, but as a consequence of the failure. So the initial buckling has got to occur, otherwise this doesn't propagate. Once buckling is started, it can travel rapidly along the pipeline for long distances through depth which the pressure no longer able to propagate the buckle. So that's rough, is saying it's confirmed what I just mentioned. So propagation buckling occurs at a lower pressure than external pressure collapse. Propagation buckle most likely to initiate due to combined bending and external pressure and tension in the sag bend during lay. So in other words, if you're doing this and I overbend it here and I've got my pressures too great here and it collapses, that collapse will propagate all the way up here till that pressure is no longer capable of propagating the buckle. So that's why we don't like buckling, and we'll discuss a few things in a bit. And this is basically the Battelle Institute, and that is a formula where SMYS is safe minimum yield, R is the radius of the pipe, which is the diameter over 2, T is your wall thickness, and these are all the different formulas that people come up with. Shell come up with their own, Battelle Institute, DNV, but they're all the same, and you choose which one you want to use. I won't go too much into buckle rest, but you can try and stop that buckle propagated by putting thick rings on. If I put a thick ring section into a pipe, what does it do? What will it do? What will
Increase
it?
the critical bending moment.
So that's my pipe, and I bend it. What have I done to this pipe?
Increase the wall thickness.
I've increased the wall thickness, so what's changed between here and here? Who said D over T? Yeah, I've changed the D over T. But I've also changed the flexural properties of the buckle rest of this section. So I get a step. Do you know what the EI is? That's the second moment of area, and that's the elastic modulus. So what I've got is a step change in the EI. So if I bend this by putting a bending moment on it, what's it going to do? Well, if I bend this, it's not a nice smooth curve anymore. So what it's going to do is this. So I thicken this to stop buckle propagation, but I can make it so I fail by bending more critically by putting that in. So this is what's called fractional discontinuity, and you can then make it, got to be sure that when you're laying it down with a buckle arrestor on it or fitting wall section, you're not overcoming one problem and making another one. So arresters are propagation. I've not known a pipeline to have buckle arresters on them for ages. It was a popular way of doing it before, but we don't seem to do it now anymore. But theoretically, when this starts to collapse, it will come to this when it can't collapse because it's too thick a wall thickness. So the buckle will stop here. It won't propagate past this. One time a day they used to put these on as rings. And if they didn't make these long enough, the buckle propagate straight through, onto the next one, onto the next one, and onto the next one, and onto the next one. So buckle propagates buckle. We don't. Labour contractors don't like using them. Well, Rich just said that. The rest is not long enough, the buckle will pass through them. Right, effects of tension. Can I just look at... It's like I should think some of this. Yeah, okay. Right. Do you want to take a break and then I can get ready for the next bit? Yeah. Has anybody any questions before you go?
Yes.
Who said yes?
I didn't. I said no. Maybe not yet.
Oh, not yet.
Maybe.
You're storing it up for me, are you? So we've got through till 1 o'clock, haven't we?
Yeah.
Long time. So what time are you going to be back here? 10, 15 minutes? Yeah, okay.
Well, we don't have to do that too much. Just trying to bring in as long as you know enough to.
Those technical laws like
Yeah. Yeah. Right, we'll get through. Right, one more to the board.
now the sleep will not come. Damn it! Difficult to sleep when it's break.
Yeah, when the weekend. Yeah, it's always like that.
Auntie!
Wow.
What the
That is okay. You don't do that. Do it.
What did I do?
You did that.
No, I was trying to sleep.
Those are
Moses. But that is bad thing. But just before that you can't wait. It's difficult to sleep during the rest.
Trying to sleep. I was trying to sleep.
You were. I can't.
Sleep won't come when he starts getting jelly. Sleep will It is a pain. Oh, on Monday.
Hey, keep. What's the problem? What's the problem?
You can start your own massage file. You can start your own massage file.
So it's in deep, very deep water, is it?
Yeah.
Explain to me and then I'll see if I can. Explain what you mean.
I mean, the pipeline here, and then this depth is like very high, and then this. Like so normally we calculate hoop stress by actually internal pressure.
Yeah.
But in case of we have the external pressure.
Well, that'll make it very thick wall, much thicker than it needs to be.
What do you mean?
Well, because you're allowed to take off. You said this. It's internal pressure minus external pressure. So that pressure is the internal one you put there.
Yeah.
Over 2T. So if you don't take account of the external pressure, you'll end up with much thicker wall than you would. If you, yeah. So that's why we can take this, because once you've laid it down, that's there all the time. You can't take it away. But what diameter is it, roughly?
So maybe 400 millimeter.
400 millimeter, 16, roughly 16 inch. Yeah. Okay. So that's going to be made out of, well, you can go up to 20-inch seamless, but it might be seam pipe. So if it's seamless pipe and smaller diameters, when you lay it from a real vessel, we bend it, there is a critical to get this right. To ensure your pipe can be reeled, that's nothing to do with actually this is bending it on a reel, it's straightening it again. It needs a D over T ratio greater than 20, less than 20. Although it's roughly about 19, otherwise it's buckles. So, but if you're going for laying it by a J-lay, what's the water depth?
But I'm talking about actually the operation status. Like in case of we have this kind of situation for the operating status.
Okay.
So like if we have a cyclic internal pressure for the fatigue consideration. But in case we have we are under the external pressures influence, so that means the cyclic pressure is actually less than.
Yes, if you've got no external pressure, then your internal pressure cycling will give you higher hook tensile stresses. But with external pressure as well, you get less hook stress cycling. But then you've got to say, well, what's this part doing? Is it going over a seabed, what we call hogging, or is it going into another one, sagging? So that needs, but then your precious fatigue cycles. You've got two sides of the pipe. If it's bent one way, then if it's in compression on one side, if it's tensile there, and compression there, get this right in a minute. We'll be covering this in a little while, and negative stress there. Then, if you've now got an axial stress in it as well, then this, when your axial stress or your pressure stress comes on, it can reduce this and increase this. So you've got to look at what happens to your material with cyclic tensile and cyclic compression. It won't be equal on both sides of the pipe if your pipe's bent.
You mean because it's in the biaxial? If we considering like a hook stress and then axial stress.
If the pipe's not bent, which is what you're saying here, then your hook stress will just be with internal pressure only, give you greater hoop, and also the longitudinal component of hoop, which we'll discuss in a minute. But if you've got external pressure, that will be less. But when you're doing fatigue, you need to take the other stresses involved, which we'll go through now. Pressure, that sort of temperature stresses, bend stresses, strains. So, yeah, it can get rather complex.
But I think, like in case of the very long subsea pipeline, the actual stress is not very high compared to the hook stress.
What's its temperature and pressure?
Temperature, like maybe 15 15, the external temperature 15 and the internal is maybe not
So that's
really-
warm water.
Yeah, warm water in the Southeast
Yeah.
Asia.
Yeah.
Internal
Nice.
fluid is just the condensate is not very high
Yeah.
temperature.
Yeah. Okay. Oh well, then so it might not be such a problem then. But we're going to go into that now. Yeah. Yeah.
I'm not clear about the equation for the sequel pipeline. Sequel pipeline, there is another calculator. What the equation? You said Lane's equation or Lane's formula?
Lame.
Yeah. Lame.
Yeah. Yeah. He's just the guy that created it. Let's. Nothing is crossed that way.
Ah,
Yeah. So you've got your internal pressure, external pressure, outside diameter, and internal diameter, and that is your external pressure.
So
So that's one part of the equation, and then you take off that pressure because stress is a pressure. So that's one calculation. Your hoop stress, and then that's the if you're not sure on this, when you have a look at it, see Narek and ask him to email me, and I'll send you some stuff with the derivation of that on it. Yeah.
And the
Well, in fact, if somebody will make a note and then get Narek to, well, when we wash up at the end, well, I'll have a list of queries, and then if you get Narek to send you an email, then I can just put some effort and send you the answers. Yeah.
And I think for the thin wall and thick wall, what the assumption is the thin wall we have a plane stress condition, and the thick wall we have a plane strain condition, because in the thick wall the strain
Yes,
Yes,
I
across
think
the
you're,
world,
it is, yeah.
But I think for the subsea condition, when we have external pressure, even we have a thin wall pipeline, the expansion across the radial direction is actually restrained because of external pressure. Do we consider that situation like a plane strain?
I'm not sure. Can you explain that one to me again? Sorry, these are yours. Aren't they?
Yeah, I mean, like for the thin wall, and this is thick wall. For the thick wall, for the thin wall, actually, the strain for this direction is like a free because of thin, and then it can expand without any stress. So in this case, the stress is zero. If this is a G direction, stress is zero, and this is a plane stress condition.
I'm not sure on this one.
Okay.
I mean, plane strain or plane stress means the stress or the strain stays constant across the section. But when you do thick wall, it obviously can't. Say plane.
Yeah, but I'm just curious about even for the thin wall, but if it is under very deep water, where there is external pressure, and because of that external pressure, this thin wall cannot expand. And then in that case, it acts like a thick wall pipeline because of the restriction.
Well, it'll expand as a function of the difference between the internal and external pressure. So you've got pressure on the inside and pressure on the outside, and you've got to balance it. If this is internal pressure is greater than the external pressure, it expands to some extent. If you took this pressure away, it will expand more.
Yeah.
But it's there. So.
The expansion is restricted because of external pressure.
So what you're saying is, if it's like, for instance, if we put a clamping nozzle all the way around, and you increase the pressure, we'll put external pressure on when it's expanding.
Do you know what is the day?
We need to think about that one. Yeah.
I think Friday.
Next Friday.
So where does this help you with your
When they come back.
fatigue? Or is
I mean, because for the fatigue, when we consider fatigue, because for the pipeline, the primary stress is actually hoof stress.
yeah.
So I'm just curious if I need to consider fatigue for the subsea pipeline, when I calculate the hoof stress, do I need to use the hoof stress calculation by thin wall pipeline calculation or thick wall pipeline calculation?
Well, does that depend on what the wall thickness of your pipe is relative to what's its actual GMT?
GMT is like a normal thin wall pipeline, less than what that?
It's greater than one. Greater than 20.
Yeah. Normal pipeline.
Yeah. Because that pressure isn't like a fixed boundary. If it was clamped, then that pressure stress will be transferred into the clamp. But it isn't. So it just increases. But it will keep increasing. But it's balanced by the external pressure. So it's actually not restrained from expanding. It can expand. Put it on a note, and I'll.
Okay.
And I don't like leaving. You've got me curious now. And it doesn't mean that somebody doesn't come along after all this time of dealing. I mean, I've been involved in this for far too long now. It doesn't mean somebody can't come along and say, look at it this way. As you'll see in a little while, one of the things that has been done as well. Some people come along and say, that's not right.
I was not expecting this to be spicy, but it's kind of.
Right. Okay, but yeah, please put me that on a note.
I see.
Is that something I would like to get for breakfast? What do you mean by getting it?
You know, he puts what he puts in, what he puts out, puts in more.
Because what happens is you destroy your fund, then the body system finds
looks for the peak and replenish. Wherever you replenish more than what you it's alright.
I'm gonna get me back into you.
I'm being honest.
Yeah, that's right.
I don't want to lie to you.
Honesty hurts sometimes.
But it's okay. Yeah, even me, I want to gain some. I'm gaining more.
Too much.
Yes. Let's see for you, yes, as you gain. Just see.
I've been trying to eat okay, to be honest. This is just because it's not.
Eating vegetables.
Onion and cheese pizza.
That's the one.
Okay. I like juices as well, but they have a lot of sugar. That's the only thing I don't like. I do, but I know it's not it's okay. What's it worth?
Some people say you drink too much coffee, you agree with it.
Have you come to be interested in
Depends on the body. They have to run the they are insane. They take advantage of the money.
Some people say if you drink too much coffee, you will die.
Another version of this
Because I know a person who is up to 95 years, she will drink coffee. Thrice or 5 times.
This one guy, like Mexico, who eat a lot. So his friends like challenged him to eat one entire little pig. An entire little pig, just 1 meal. Well, and he did that. His stomach blew up.
It's still wrapped up.
requires a lot of
Something else.
lecture over here.
But you know, is it a bet or something like that?
What?
You need to
Is it a bet for money?
You know, I'm a
Did
big
they,
depends upon the company.
was it a bet or you just want to try it?
He just wanted to try it.
Yeah, but you want to
No, if it's for money, it's like
So that was my choice. Yeah. We used to. So, but I've done quite a lot of work on limiting strain and the mistake. Get more to. It's not like they're going to but thanks for this.
I think he used a lot of chicken.
especially if you are doing this, they will ask you to maintain it. When I was watching, they gave me a diet chart. I should follow this diet. Which I don't want to change. I was not following
Yeah, I eat a lot of bread.
Shall we start or? I don't know what's happened to the three at the back. Two at the front. Where do they go? Do they have to go far? Right. I don't want them to miss it really. We'll wait a few more minutes.
Your body is there. I don't feel much.
I mean, that is
Have you got one for me? So we've got these, just this check. How many have we got left?
He's not bagging a couple of minutes, just get going.
Yeah. Well, we'll give him another minute. We're just waiting on the one, are we?
Yeah.
Anyway, I'll start this session off because it's the last one, and I have a bad reputation. The predecessor to Naricor was Dr. Julia Race. I've got a reputation that precedes here, so. But to say when you are an actor or something like that, or on television, you never work with animals, and you never work with children. The golden rule is when you're lecturing, you never tell a joke. Okay, so you're going to get a joke. So this is about being an engineer, and why it's one of the best professions in the world. But we have an English expression about, and it's a Yorkshire expression about having a nous, logical thinkability and thinking. So what you've got to do is just in your mind's eye, picture going back to the French Revolution. And the French developed that wonderful machine, guillotine, la guillotine. So what you've got to do is imagine yourself in a square in Paris with this guillotine. And in the corner came a car with 3 men, an accountant, a lawyer, and an engineer, all up for execution. So the cart worked its way around to the guillotine, and the first one they took off was the accountant. So the accountant was taken off, and he was taken up the steps and put his head into the guillotine, put the clamp on, and this pull the lever, and the guillotine chopped down, and just that much above his neck. So they said, well, the rules are, it doesn't execute you, you go free. And this was off, so the accountant went free. So the next one up was the lawyer. So he walked up, put his head down, clamped him in. Lawyer went down, same thing, stopped this much above his neck. And he said, you sure you could go free? It's not executed. So he got up and went away. And then it came to the engineer. And the engineer, they brought up like that, he was coming up the steps. And he looked and he says, oh look, I can see where it's sticking. Think about it. Oh, the engineer said, oh look, I can see where it's jamming, where it's stopping.
He just killed himself.
That's not gone down very well, has it? Right.
No.
It normally gets a much better laugh than that. Right. So we'll carry on. There's only just Chappie's probably gone. So this is where we finished off. So effective tension. So if I've got a pipe that's under pressure and a pipe that I'm bending, then if I apply tension to it, So we said when we bend it, it goes into tension on the top and compression on the bottom. So if I apply tension onto it, what I'm going to do, I'm going to straighten it, aren't I? I'm going to stop it from bending. And that's what we do when we lay a pipe. We lay it over the present, we apply tension to it, so we control the bend. So we limit the bend, and therefore we can control the how much we buckle it. So tension helps the buckling. So we need to apply lay tension. So longitudinal stress comes from pressure. How does the pressure give us? If I've got pressure on the outside, how does that give me a longitudinal stress?
There'd be two, wouldn't there? There'd be end cap, but also there'd be, if you get hoop strain, Poisson's ratio would make the pipe on the contract.
Right, so you're going to get a longitudinal component of the hoop stress. So if you've got compressive hoop, and you will get a compressive longitudinal component, which is the hoop stress times Poisson's ratio, and that's what you'll get in longitudinal. Then the end effect, which is afternoon. So the end effect is if I've got a pipeline and well, I think I'll just let the slides run on. We call it the end effect, but you're right, you've got internal pressure and we've got external pressure, which will act on the ends of the pipe. And temperature stress and residual stress. Residual stress means when we lay it, if I'm laying the pipe and I'm applying the tension to it, it stretches it along the seabed. And if I take the tension off, it wants to go back, but it can't go back because the friction of the seabed won't let it go back. So you always end up with a residual tension in the steel. So let's go through it. Longitudinal hoop stress, longitudinal stress due to pressure is the hoop stress, as we've defined, and the longitudinal component is the Poisson's ratio times the hoop, and where that is the Poisson's ratio, and P is the external pressure, D is the outside diameter again, and T is the wall thickness. So it's that's basically it. What's happening here? It's just transposing. So if you could have put the hoop stress as PD over 2T, but then this one's just used the D as R over 2, so it all cancels out. So that's your hoop stress, PD over 2T, times your Poisson's ratio, which is your hoop. The end effect is not just the pipe at its end. Its end will be like this, with a pressure, that internal pressure is that way, but there'll also be an external pressure. If that pressure was zero inside, I'd have the external pressure acting on there. So, but that's just on the end cap. Do you mean there's not a button you can press?
Sorry?
Is there not a nice button you can press so they all
No.
come? Oh dear.
Can I go?
Yeah, sure. So I'm sure we have to all go sleep. It's alright. We've been waiting all winter to see the sun, and now you're shutting it out. So, but also when you've got, this is overemphasised, I've got a pipe around the bend, whether it's an elbow on a spool piece or a riser, or a curve in a pipe, and I've got a pressure on the inside, that pressure will act on an equivalent internal area and we'll try to put forces on that way. So that's the end effect there. But so it doesn't have to be the very end. So in the middle of a pipe that's got a curve, there can be an end effect that will be in the pipe. There is another one that is often ignored, that if I've got a curve like that, and I've got fluid flowing around it, I've got shear stresses on the wall, and that shear stress around the wall can actually give me the difference in shear stress here can actually give me a force in that direction from the shear. But I've not included that in here because, but other than to tell you, it does occur. Right, temperature stress. If I take a steel bar like this, you're going to like the animations on this. Right, if I heat it up, what's it going to do? Like that. Right, so if I've expanded that, so it's gone to a length L plus delta L, and we'll see in a bit how you calculate your delta L. So what's the stress in that bar? Well, you told me earlier on. So what's the strain in that bar? What?
Delta L by L.
So we know strain is extension over L. So in that one, what's my strain in that bar?
Changing.
What's the strain? You three at the back. What do you say? See, terrible. Right. What's the strain in that bar that's being heated up? It's grown in length by delta L. So what's its strain? Is it delta L over L?
Yeah.
Who says? All those that say it's delta L over L. 1, 2, 3, 4, 5. 5 out. I don't know many, can't count. So if we're now assuming that, and that's your stress strain curve. So I've now got somewhere up here a strain which is delta L over L. So what you're saying to me, if I've got a strain of delta L over L, that bar's got a stress of that in it. Yes? No?
Yes.
Who says yes? Any more advances on just the one? Or two? Right. 3? Right. Okay. But actually, its stress is 0. It's just expanded. All the molecules have just stretched themselves out. It's not under stress at all. So, stress is 0, but strain's not. So, the actual stress is 0, and my actual strain is delta over L. But it can't be correct. There's no materials properties for that.
One's bringing about the extension.
So what it's saying is I've got a stress with no strain and strain with no stress, and that can't be. So the only way you can get a stress in this bar, pardon?
We need to constrain it from both sides.
Before you expand it. Yeah. Or similarly and equally. Oh, but we call this apparent strain, because it's not really a strain. It's just grown in length. If you put a pressure on that, or force on the end, and push it back to its original length, so now it's got no strain because its L is not increased anymore, but you've got an actual stress, P over A, and you've got an actual strain of 0. So the only time you're going to get a thermal stress is, as you're saying, when you constrain it. Okay, so we'll see in a little while, if the pipe's free to expand at its ends, at the very end where it's fully expanded, there'll be no stress. And at some point back in the pipe where it's stopped from expand, it's going to have a thermal stress. So that's the nature of thermal stress. So you can have an actual stress. If it freely expands, there's no stress, and there's not really, it's just an apparent strain. If you constrain it, you've got an actual stress but no strain. So delta L is equal to alpha L delta T. So what's at alpha is the coefficient of thermal expansion, linear expansion. So delta T is your increase in temperature. Alpha is your coefficient of thermal expansion. And therefore actual strain is delta L over L. So if I take that top part of that equation and bring the L on under, so I take this L from here and put it under there, that's my apparent strain is delta L over L. So you now end up with your actual strain is that, so the L's cancel out, it's that. So at E now you can put in actual stress over actual strain, where actual stress is the actual thermal stress. It's E times the actual thermal strain equals E alpha delta T. So, what's that telling you? What's it telling you?
We're using the modulus of the material to get the stress.
Look at this. What's it telling me?
Assuming it's remaining in the elastic zone at all times.
Yeah. But more importantly, it's not a function of length. Length gone. So it's a function of E, which is constant. The temperature rises, change. So that temperature is a change from your atmospheric seabed temperature to your operating temperature. So if your seabed temperature is 4 degrees and your temperature when your pipe is running hot is 60 degrees, then the temperature difference that you have to use in this is 56 degrees. So it's not a function of length. So it's independent of the length. Okay? So, but if the pipe is fully restrained anywhere in its length, and we heat this pipeline up, you're going to get temperature stress. So, this is a rubbish drawing of a lay barge. So we did say to stop it from buckling, we apply tension here, and we get equal opposite tension there, because it's like a space frame down, and it's got to have that. It's balanced. And that's how we used to do a lot of analysis in the early days. But as the water depth got greater, we found that we were buckling pipe too often. So one thing we questioned is, was that tension actually the horizontal component of it? So this one, if I'm applying the tension up here, like a lay barge, then that is the horizontal tension. You see that, you realise that, do you? So if I've got the top of the pipe coming down like that, and I apply tension there, like in a J-lay, then that is the horizontal component of tension, and that comes round to there, and that's TH. That tension is not seen here. Only in shallow water does it be seen to apply. So, the way that we used to do it is, when this pipe went underwater, its weight per unit length was its submerged unit weight. Do you know what submerged unit weight is? No? Right, we better make sure you do. If I've got a steel pipe, that's going to have a mass. So be careful when you're working out the difference between mass and weight. Make sure you understand the difference. So, but if I take the volume of that pipe per unit metre, multiply it by its density, I'll get its mass. So I'll have a mass of steel actually down there. Steel. Then if I put a coating around this, and I'll just draw the one coating. So I'm also going to get the area of this coating times its density. So this is equal to the area of steel times density of steel. And this one is M coating equals the area of the coating. It's actually the volume per unit meter length, but the area of coating times row coating. Okay? Now I've got a mass. Now, if the pipeline's lying on the seabed with an air in it, we just forget about what's inside it. But if I now fill this full of product, I'm going to have mass of the product. So I've got M product acting down there, which is M product equals the area of the product times the density of the product. And if that's an oil, stabilised crudes, typically 800, 850, something like that. And if it's gases, 160 kilograms per metre cubed. So these are all masses. Now what else have I got to consider? Well, I'm going to put this in water. So what's going to happen to it? Displacement. Right. You must have heard of the famous scientist called Archimedes.
Yes.
Right. So I've got these three things, but I've got another force going up there, current mass, which is my displacement, and that equals the area, the external of the pipe, which is this area times the unit length times density of the water, or C, I'll call it SW. Some of this is all in those technical notes you want to look through. So, at any point, if I put this on the seabed, if this is greater than these three added together, what's going to happen to it? Float. Right. So, if this is not as great as these three are greater than that, then it'll have a downward force. So be careful of your units. We call that negative and that positive. Positive buoyancy, negative mass. So when you've got all these masses, if you want to start turning these masses and using them in formulas like bending moment formulas and that kind of stuff, you need to turn it into newtons. So you multiply it by G. Okay, so again, so that's your displacement. Right. Now, having understood that, the way we used to do it, we used to work this out and say, right, it's got a submerged unit weight, which we call it you can call it a submerged mass, and then you multiply that by G times G equals a submerged weight. So what we used to do is to calculate this and put this into two beams. That's how we used to do it. We used to take a beam here, one beam, and we'll lift it up. And we take another beam, but the radius of that beam was controlled by this stinger. Except when it came off the end there, then it would do that. And then what we'd do is find a point here where the properties of one beam were equal to the same end properties of the other beam. And that was a point contraflection, and that enables us to work out the geometry. And that's how it used to be done. So, if you say, right, to yourself, if I now take this, and this pipe is coming down, and it's going to very considerable depths, I've got bending, I've got more tension, and this component of tension gets less. Why does it buckle? So in other words, this, we've taken this beam, we made up here a beam of a submerged of a unit weight equal to that, all the way down the length of the beam. But it's not true. This assumes, and this is where Archimedes was right and engineers got it wrong. If I take an element out of this pipe and I apply the mass there, or its weight, submerged weight, its displacement, that assumes, Archimedes saying, that displacement is the weight of water displaced. But when it's in a beam like this, it's not displaced, because the pressure is not. The pressure actually not to make that. If that was just a steel cylinder, and I apply pressure on there, and pressure all the way around, then Archimedes had got it right. But if I take that cylinder and then I say, well, that's part of a long pipe, that cylinder's take the next cylinder and the next one and the next one, that pressure there, acting in that direction on that cylinder, has got to be equal to the pressure on the next cylinder in the opposite direction, so they don't cancel each other out. So, but these are joined, so those pressures can never be applied. So, because they can't be applied, this beam theory in deep water, with a deflected beam there and depth, doesn't hold true. And theoretically what you're supposed to do is you take this and you start working out the buoyancy, vector displacement as you go down. What you'll find, and again with risers, if I've got a vertical riser, and there's definitely one in that technical notes you've given in there. If I've got a vertical pipe, let's put it this way. If I've got the ground, concrete, and I cast a vertical pipe into it, into the ground, so this is totally solid. What's the stress there? What's the stress in here? This is in air, so forget about atmospheric pressure because it's so small. So I've now got a mass of this pipe acting down. So if I take that mass, or its weight, equals its mass times G, and I divide that by its cross-sectional area, then I'm going to look at the stress. Yeah? If I turn that upside down, what's the stress there? Oh, let's go back. What kind of stresses am I going to get there?
Compressive.
Compressive. So this stress here equals the weight over the area, and it's negative, and therefore it's compressive. This one,
Same but positive.
Tensile.
so it's exactly the same stress level. The magnitude is exactly the same, but it's in tension. So you all accept that? Good, good. Right. I'm going to rub that one off because I've just put that on as a method of explanation for you. If I do that, and I flood this, let's say this is in the somewhere, and I flood it with water to here, so it's exactly right across the top. So this is water. What's happened to that stress?
It's going to be reduced.
Anybody?
Probably remain the same.
Who says it's going to reduce? Is it? If I fill this full of, if I put strain gauges on the inside of that, and then I flood it with water, what's going to happen to that stress? Because without the water, I'm measuring a negative compression stress. And I flood it with water, what's going to happen to its stress?
I think it's usually the same.
Is it going to reduce, or is it going to stay the same? Right, come on, let's have a vote.
Should be the same.
Best way to sort it out is a vote. Those in fact to say it's going to stay the same. 1, 2, right. Those that say by the saying it's going to reduce. Somebody says this is worse than the Scottish referendum. Right.
Have another vote.
You can have another vote. Right.
You're going to lose some of the buoyancy. So it's going to press harder down.
There's no weight on actually on the top. Avogadro's laws of pressure, that'll be the same. There's no buoyancy to it when it's vertical. So what we're saying is, when the pipe, this pipe here, gets more into the vertical, the buoyancy is less and less. So there's a lot of pipe in here that can actually be its dry weight. And that's what we thought by pulling on it, we were changing its curvature. And we were going to reduce, putting tension and we reduced its buoyancy, reduced its buckling. It didn't. We found that one night when we buckled it 8 times in 1 week. It was a major headache. But that is in those notes. That's definitely in those. Yeah.
Excuse me. If that pipeline were, let's say, horizontal, then the stress would be reduced? Or
Then
would
your
this-
weight would be reduced. Yeah. Yeah. But then whatever tension. So what we're saying, this tension here, the horizontal tension of this in deep water can actually never occur. Can all be very, very low. So we're not getting residual tension to it. Now all this residual tension is if I pull on that and the end of the pipe is stretching, and therefore it scrapes along the sea, it stretches the seabed. And then when you take the force off, it shrinks back. But it doesn't shrink totally back. It leaves you with a certain percentage in there. And we normally say 10%. Okay. So Archimedes, people said, oh, when we first started doing that, oh, you're saying Archimedes is wrong. We're saying no, we weren't saying Archimedes is right, we're saying you were wrong. And there's a big difference. So therefore the change in longitudinal stress actually constrained pipe after lay is the actual stress and strain in the is 0, and that is basically the force, the stress in the pipeline. So the first part here is that part is your hoop component, so that's your hoop stress multiplied by Parsons ratio gives you the longitudinal component. This is your residual, is your thermal stress, which is not a functional length, and this is your residual. So this minus this plus that gives me the stress in the pipe. Okay, this is not considering bend.
A question in there. The reason that the thermal component of the axial longitudinal stress is negative is because it was installed in a lower temperature, hotter temperature, and then it went cold.
Well,
why is negative?
The other way around. This temperature, when you lay the pipe onto the seabed, you lay it down, it settles say at 4 degrees, or in some nice warm climates around the world, 14, 15 degrees, and then you heat it up to 100. That's your temperature, is the temperature difference. It's not your actual temperature of your product inside. The temperature difference between inside and outside. But if you've got thermal insulation on it, as we'll see in a little while, your temperature on the of the steel is retained much more closely to your internal temperature of the fluid. So that you have to be very careful using that, because theoretically, if it's got a perfect insulator on it, your temperature on the outside of it is the same as your seawater. Okay, longitudinal stress. How are we doing? Longitudinal stress includes residual longitudinal stress and lay tension. Watson's effect, you've got that. So dependent on the force profile, that depends on expansion spools reactions. So if I've got a pipeline if I've got a pipeline and this, if it was free, at the end would want to expand, say to there. But I'm now going to put it with a flange on the end. And put it in a spool piece. Terrible design spool piece. So, depending on the design of this, that will oppose the movement of the pipe. So we need that effective length extension and the stress there, so we can design the force into this spool pieces. And that's why we do it. And that's called the expansion spool reaction. Frictional force build-up of the expansion zone. Strain force, which is defined by operating pressure, operating temperature, residual lay tension. The actual force, right. So we've now got a pipeline, hot end, inlet, cold end, outlet. So this is going to want to expand more than this end. So this will be expanding more than that end. But if you've got the unit weight of this pipe multiplied by the friction, longitudinal friction factor, when you've got the balance of the total weight of the pipeline times the friction. So in other words, if I take the mass per weight per unit length multiplied by friction factor, and it gives me a figure, and then I know the total force in the pipeline, I can then divide one by the other to tell me the total length. When the forces and that friction balance out the force, and it stops moving. And this is called a virtual or point of no movement. And the same at the other end. So you get that, the actual force. So these are expansion zones governed by friction, restraint section governed by temperature and strip pressure. So you can see that from the hot end it's higher actual force than it is the lower end towards the out, because it's lost the temperature. If you put a lot of thermal insulation on it, this wants to go up, so because you don't lose the temperature. So what you've got to do now is combine all these stresses. You've got your end effect, which is that, pressure times the area. You've got your restrained actual temperature stress, which is that. You've got your hoop stress and its longitudinal component, which is that. You've got the bend stress. So now, if your residual stress is 0 from tension, you could bring that into this. But I've got now an actual stress from my pressure. I've got an actual stress. That this one over here is in tension. This one here is in compression. That's in tension, and that is in both compression and temperature. And that's why I said it's two values. So this one, I think that might be the wrong way around. So I think that diagram's the wrong way around. This should be in tension. If PI is greater than PO, it wants to expand that way. So that's the wrong way around. And then the longitudinal hoop component, if your hoop's constant, internal pressure and external pressure. And then that one has two values. So if you want to know the stress at the top of the pipe, that's the wrong way around. It should be that minus that plus that minus that, and then the same thing, add them up across the bottom. So you end up with two values of stress. When you've got that stress, that's the actual stress in your pipe. Oh, I've got my residual stress. So you've got to add them all up, do a vector addition, top and bottom, and you end up with longitudinal stress. But then you've got to put it into an equivalent stress. Does anybody know what von Mises is? Yeah? It's the theory of failure, but there's a formula for it. And the one we need, there is actually a shear force in this, but you notice in none of the formulas have we taken shear force into account. That's the shear force that way through the pipe. We don't, because it's so small. So you can use this formula, and basically you get von Mises ellipse, and just like that failure ellipse for the buckling, you can now take this. I just want to go on one. If I do the ellipse, this works out amazing. And that's 0, 0. So this is hoop, and this is axial. Well, I've got no other loads, I just put pressure in. I'm going to generate a hoop stress so that I can have a stress up here which is equivalent to the hoop stress. But I'm going to get a longitudinal component of it, which is the hoop stress times glass on. So I've got a line that comes up in here. So, if I take this stress up to here as a hoop stress, then my stress, and I've got nothing else other than pressure, then I can end up with a point there where that is sigma hoop times Parsons ratio, and this is sigma hoop. Now, to stay within this ellipse, I've got to do one or two things. I've got to make sure that that cumulative stress never comes outside this ellipse. So I can now, if I now add, I've got no temperature, and I put longitudes, that means I can put that much longitudinal stress into the pipe before I go over this board. If I put some compression loads in, I can go from there to there with compression. But if I've got temperature, I've got compression in here, so I'm already I'm already over here somewhere. And that's 10. And that means if I've got anything stretching it, I can only bend it such that amount of compression goes into it. I can bend it such as that is the bend stress and tensile, but I can only bend that. But when you start putting all the other tensions, this tends to come back over here. And so what you're doing is you're making sure that all your combinations of your stresses stay within that ellipse all the time. Won't bother with this. You can look at your notes. Strain-based design, don't worry about it. Limit state design, don't worry about it. Stability. Right. It's a good start. That's a pipeline sitting on the seabed, and it has a submerged unit weight. So make sure you know how to calculate that. Density of steel. In any exam, if you look at the other exam questions, I give you all the values, I give you your densities, I give you everything. I set the answer.
Formulas. Formulas.
You'll get plenty of formulas. But beware, some of them are not needed.
Yeah.
I'm not that daft. So I can actually, for a price, I can tell you which question you've got to use the formulas in. But it comes very expensive. No, joke. So I'll show you one in a bit. So let's talk about stability. So who knows what a wave is? How do waves form? Have you done wave theory?
Yeah.
Oh, you're experts. Right.
Third 99.
So you can explain to me what a superwave, how a superwave comes about then. Who says yes, they can explain a superwave? What causes waves?
Dynamics of offshore.
There's a big wave making machine on the other side, on the other side of the channel. It is generated by the interaction of wind over the waves, and it's over the top of the water surface, and it pulsates it and lets it up and creates waves. And basically a superwave is, we know now we've got the satellites and things, you can see when a wave travels, it can travel thousands of miles. It's been known to travel 3,000 and 4,000 miles. But people think that's a long way for the water to travel. There's no water moving. A wave is not a mass movement of water. It is basically an energy transformer that lifts the water up. So we'll look at that in a bit. But the mere fact that you have waves that come from different parts, different directions, if you've got the theory of light, which is Newton's theory, and you pass light from different wavelengths through different points, you can actually produce shadow. You can produce Newton's rings, light and dark. And it's the same with the energy of the waves. The waves, if you've got 2 or 3 waves that all come together, so they're all peaking at the same time, at the very same point, at the same point in time, you get a very high wave. Otherwise, they can cancel each other out. And that's how the superwave comes. So, stability. Why have we got to design it to be stable? Well, the very fact that you place a pipeline on the seabed, you change the water flow patterns over the top of the seabed. So what you've got to do is make sure that this elongated pipeline doesn't move. It's stable on the seabed. So we'll do that. There are more ways of doing this that you can possibly think, including some mine. But all we're going to do is consider one method, and it's the basic. So you don't have to worry about anything else. So, but the waves cause vortices and movement, and they scour out the seabed. They scour out, and then suddenly, as you see on this one, it goes underneath. So the hydrodynamic force is tidal current, comes from tidal current, storm surge current. There's a very good demonstration of storm surge by a guy down at Southampton University, and he has a big plastic dome, and it floats on top of the water, where the ends of the dome are just into the water, and he sucks a vacuum, and the water comes up inside, and then he can move this bowl anywhere he wants in a big bath of water. And that's exactly what a storm surge does, because when you get pressure drop, the water lifts, but then when it lifts, the water's got to come in from the sides, from all different directions. So but storms travel, and so you can get a storm surge effect on stability. Depends where it is in the world. Sadly, we get tsunamis, which are, as you know, sadly, when you get what do they call it, seismic movement, and you get earthquakes under the seabed, and lifts up massive millions and millions of tons of water, and that has got to flow somewhere. But I don't think you can design a pipeline to withstand anything like that. Wave-induced velocities. So hydrodynamic design, stability design. I've got waves and currents acting on the pipe, and we'll explain what they are in a minute. And so therefore, if I take that, I've got my lift, which is this. That has got a downward weight, that lift is the hydrodynamic lift, okay, and that's the hydrodynamic drag and the hydrodynamic inertia, and that is opposed by friction on the seabed. So classic static stability is what all we're going to do. So this, if you go back, this friction resistance here has at all times got to be greater than that. But this is affected by, this friction here is affected by that lift. And in this way we don't allow for any movement of the pipe. More other ways of doing it, they allow for certain movements to allow it to move one way, and then they say, well, by which time other movements it's brought back again. Don't worry about any of that. Classic theory all the way. Design currents, we'll flash through them. 1/7 power law, logarithmic profile explicit. So if you've done wave theory and tides and movements, design wave definition, significant wave. A pipeline we design is a long, slender structure, so we take the significant wave and not the maximum wave. If it was just a piece of cross member on the base of a platform, we apply the maximum wave to that. But with a long, slender pipe, so in other words, we're allowing for the pipe to try to be moved at a small area, and it wants to resist it in other areas. So we use this significant wave. Maximum wave. Was there any calculations in that I gave you in that pack? There was one I gave you on stability analysis. We'll have a wash up before you go, and then anything that you're not clear about, if you put it on an email, give it to Naracorn and he'll send it to me. But to be honest with you, this is too complex a thing. I could probably give you an exam question on this and you'd spend all your day on it. And so I'm not that cruel. So, but it may be that I want you to know how it's done and why it's done. Wave theories, aerostokes. There is this, you can work out which wave theory is applicable. It's all non-dimensional parameters. When a wave goes over the top of a pipeline, the wave is going up and down. And although I said there's no mass transport of water, the actual particle of water, have you ever had the wave tank going down here?
No.
Because we used to do an experiment making these waves, then we drop particles into it, and you could actually see them going round. But I think maybe they got clogged up the pumps or something, I don't know. But in deeper water they become circular, and in shallow water they're more elliptical. So the top of the wave, that's your current. The only way you're measuring current is we put current meters in, certain height off the seabed. And once we know that height and that velocity that records, you can then use this law to work out the height Z, top of your pipe, and that's how you work your current out. But, so, we take currents to be tidal, steady state. As you know, in certain times when the moon and the sun pull together, you get spring tides and you get the higher velocities, you get the higher forces. But it occurs twice a day, it's 2 times a day. So it will only peak for something like 6 hours, twice a day. So therefore we take it to steady state, we assume it constant. The wave velocity is in shallow water, it's the green, and we take it as sinusoidal. And then in deep water, the wave velocity is diminished. But there will become a point when it drops to 0 in certain depth where there's no wave effect at all. But in deeper water, in shallow water, it's that, in deeper water it diminishes that. So now, if you take this over any wave cycle, you can now add these things together. So, if I take and add these together, I've got that plus that and that to add together. Yeah. what you've got to do is take the vector addition, because in this part from here to here, it's going the other way. Your current's always going in one direction, except that 6 hours later it's coming back again. But in your wave cycle, this half it's going the opposite direction. So what you have to do is you get, I won't go into this because this is 3-dimensional waves. So what we're after, traditional wave is Morrison's, and you are looking at through the step of the wave. Let's go back again. If you look at what I've done is across the top, I broke it down in any wave cycle, one orbital path from top to that again. Basically I've taken that as a circle, and therefore it has 2 pi radians. And that's my period, that's my phase angle. So what you have to do is you don't know what that critical phase angle is, because it's a function of this. So what you have to do is work it out as a table, and I thought that's what came up next.
Excuse me, sir. So from your explanation here, does it mean that the current velocity of the shallow water is more dangerous than that of the deep water?
Could be. Could be. And in shallow water, how shallow are you coming up near the beach? Because when you get near the beach, when the wave height is 7/8 of the water depth, the wave breaks, and the mass of water then will run to the shore. So, but yes, it could well be more dangerous than in deeper water. Stability is not so much a problem. The one you're concerning yourself with is the traditional. So that's that formula we said. Again, this is your weight, your lift, times your friction factor. It's always got to be greater or equal to the inertial lift, inertia plus drag, times the safety factor. So it's always going to stay where it is. And there are all the formulas on there. Can you check? I did put some example calculations of stability. There's a whole very early question, and I gave it through, and there's example calculations of the stability. But what you need to do, whoops, there's your forces. You've got to look at accelerations and velocities through the phase. That's your vector diagram for forcing. But what you can see here, with time over one wave cycle, this is your drag, your calculated drag from Morrison's, measured drag but measured lift. Then it's not now nice sinusoidal, it varies considerably. And your coefficients of friction to resist, that's the mu, varies on the geometry. If I put it sitting on the seabed, I can't give you these values because they're part of some private research. So the drag coefficient for that will be different from that, from that, from that, from that, from that. And if you put it in that, but the only problem is when you design it for that, often pipelines will walk up the side and they end up being on the seabed anyway. So this is the chart that's in here. So this is what you need to do, is produce yourself a spreadsheet, put all the forces in and step through the different phase angles. As you can see, here's your phase angles, and you step it through from 0 to 360 degrees or 2 pi radians. And then what you've got to look at, across the bottom, where you've got to set the minimum safety factor, which is that fella there, 2.33, that's got to be above the figure that you want. You've set this now. So try to do all that in an exam. It's crazy. A day's workshop, yes, that'd be different. You do a workshop with some chap or other, I don't know, I've never met him yet. You do a workshop, don't you?
I think so.
Yes. Yeah.
Seminar.
Okay. Spans. Again, this is a very complicated problem. Spans occur undulating seabed, longitudinal profile, local imperfections, contour, bottom roughness we call it. So when we lay it on the seabed, it's a regular seabed. Erosion, and you can have all sorts of conditions that we use, beam theories. None of it is really relevant now, but as it was. We now do it with advanced computer modelling, and we can model the soils, interaction of the soils in the pipe. But if you've got two spans, and two spans are close by each other, if they're very close together, the vibration of this can go through to the vibration of the other one. So they're interrelated. Now, why do they occur? Why do spans? This is the Galloping Gertie Bridge. Well, vortices, you can see in those, as the velocity increases, the vortices on as you go on. Here, you've got vortices forming on the side. Here, you've got a pair. So when they detach, the pipe wants to oscillate that direction. When you've got one vortice that side and this one's detached, then the pipe wants to oscillate that direction. That is inline flow, so it's in line with the velocity, and this is cross flow. And you'll see in a moment the cross flow is much worse, it's by far the worst. You can look through these at your leisure. There is a theory called reduced velocity theory, and if at a certain reduced velocity the frequency, natural frequency of the pipe is equal to the frequency of which the vortices are attaching and detaching, you can get resonance. Everything in this room, you, me, everything in this computer, everything's vibrating. And if you vibrate it at a certain frequency, it'll resonate and amplify it. And the pipeline's the same. So that's inline vibration, that's cross-flow vibration. There's two charts in there. One is when you've got cross-flow, so you can see the amplitude, the cross-flow amplitude, and that's your inline. And I think you'll find that the cross-flow, it can be the inline can be 0.1 of the pipeline diameter, whereas the cross-flow can be 1 times the diameter, so it can oscillate a full diameter. Now this is when, if you've got a spanning pipeline, your fatigue And the stress cycling has to be looked at very, very carefully. So it isn't just what you've got on the pipe sitting on the seabed, it's what's going to happen to it. And you get fatigue damage. Right. Thermal upheaval and natural buckling. If you've got a pipeline that's sitting over an imperfection, and if this pipeline here, some distance back here and some distance that side is fully restrained, but we've got a locked in stress in that pipe, it wants to go displace the pipe, and what it does, it just buckles it upwards. Or if it's lying on the seabed, it can buckle it sideways, and that's called lateral buckling. But it's all contained by friction. So total friction force resisting expansion that is on either side. It feeds in from the point of no movement, and it occurs in the flow and buckle when the net compressive load in the pipe exceeds the pipe bending stiffness and the pipe external restraining force. Vertical force occurs if the pipe's preferential lateral mode of movement is restrained. So in other words, if it's in a trench, its lateral's restrained, it's got to go somewhere and goes up. And those forces are not small. It can be thousands of tons in a pipe that size. If the force is to reduce, the effect of the force is to reduce foundation reaction to crest regions and can press it into the troughs as well. At certain load levels, no adjacent equilibrium may be possible, and the pipe must jump to a different configuration. So in other words, it's fully stressed up. It's really wanting to go somewhere, and if anything restraining it, if that level of restraint falls off, it'll just go. It'll snap up till it's new. And if it's restrained in such a way, it might just snap and overstress. And there have been cases where they've been overstressed and they've been shut down, and there's virtually no way of reducing the bend because they've been grossly overstressed. You can just thumb through all this yourselves. Why it happens is high levels of restrained force, vertical imperfection, and out of roundness. In other words, it's doing this on the seabed. Effective pressure, plus an effect, the pipe expands radially, thus contracts actually. It's a curved pipe, and when you bend it, the outer surface is longer than the inner, and therefore there's a radial force, and you've got to model the end cap effect. I think you just better thumb through this because we're going to, because I want to get through to other more critical things for you. If you don't put enough soil on the top of a trench pipe, you just push it up out of the way, and then you really are stuffed. So, mitigation upheaval buckle, you can trench it, but If it goes in a trench and you don't backfill it, then it's going to try and ride up the side of the trench. Trenching and backfill, so in other words, you put the soil back that you dug out of the trench back on the top of it, but that might not be heavy enough. So you trench in your rock dump. Sometimes they put pipe on the seabed and they'll have dumped rock for miles, rock on the top of it to stop it from moving, in theory. It doesn't actually stop it completely. So rock dumping, selective rock dumping, reduce inlet temperature. Well, you don't really want to reduce your inlet temperature, but if you can operate the line again, you might show, well, if I reduce the temperature, I can then bring the stresses into the allowable level. At least I can produce something, but it's not the same.
Sorry, some questions. Rock dumping, what sort of rock are we talking about? How big do they have an effect on the concrete coating?
Well, they're normally big stones. There's half of Norway is on the sea, but North Sea, in the North Sea on rock. And they start off, sometimes they put smaller rock on, because when they first did them, they knocked these big rocks on and they just damage the pipe. So they put graded rock and then the big ones go on top. But there is a danger of you damaging the pipe, and once the particular coatings, and once you've done that, once you've dumped your rock, the pipe's out of sight. You don't know whether it's damaged or not. You can't see it. So that's if it's in a trench. That's another trench. You can design it with a wide base to the trench so that it's got some lateral movement. You can backfill it, or you can rock dump it. We can do selective rock dumping. So in other words, we can work out where it's going to buckle, and we'll put a mile of rock on it, and we'll go several miles, put another mile of rock. So we're forcing it, we restrain it in those two rocks, and we can allow it to move and snake in between. So we're controlling the potential for buckling. So you can either dump it all over, that's the force that we worked out before, and again we said the delta T is your actual wall temperature of steel minus the ambient temperature. And that's the weight of soil or rock that's required to hold it in place. So you've got that formula. And this is when you've got a short length of line. So this is your inlet and that's your outlet. And normally, because of the temperature, if this line was long enough, it would expand, stop moving further back. So you've got two virtual anchor points which are overlapping. So there's one in the middle. But what you try to do is you can make it so it buckles and not buckles, but you can make it deform in the middle. And if you allow it to deform, then your force drops off. If your force drops off, it's not likely to buckle. So the other way of doing it, you make a note of, is we can lay the pipe in a progressive S, which you do anyway, because normally you lay the pipe, but the lay corridor is so small. But when you're doing S lay, you're snaking it out quite a few hundred metres either side. But the one disadvantage of that is it's more pipe.
Excuse me.
why do we want the pipe to snake while we're doing the selective rock dumping?
Well, you might not need to do selective rock dumping at all. There is the other way that you want to make a note of, because there is a way we've just done down in South Africa, and it's basically, rather than rock dumping and rather than S-lay, what we've done a little bit of a snake, but we've put concrete sleepers on, and we've laid the pipe over the concrete sleepers at certain selective points. So what we've done is we've made the pipe rather square, and then when the temperatures come on, it's designed so it goes up but sideways, and then it's taken up a deflected engineered shape, so the force has gone out of it, so it doesn't buckle. I'm not going to go through your flow analysis because that's all followed. Again, there should be a section of notes on mine on this in there, so I won't go through this. See, all this part is another series of lectures, but what you need to know is, if viscosity, if you've got this from this point up here, viscosity is a function of temperature. From here down, it's not a function of temperature only. There's a function of temperature, but you get all different curves. Why would I get those curves? You don't look the type that do much decorating. Paints, non-drip paint. And you get a paintbrush and a tin of non-drip paint. And if you stir the paint, it turns liquid. And then you let it settle it, he'll back up again.
That's non-Newtonian flavor?
Yeah, it's shear rate dependent. And that's what you've got. So, but that's all in those notes. I'm not going through any of this because you can follow the notes. But you should have done all this in a basic engineering degree somewhere. This is all Moody diagram, friction factors, Reynolds numbers. So I won't go through that. Darcy, yeah. See, he knows it all. Yeah. Is he a genius? Yeah. Is he a fan of yours?
No.
It's the boss.
Where's the boss? But in there, they're quite relevant. There are a number of formulas for working out your friction factor. But they're all based on one thing: assumed constant temperature along the length of the line. So I won't go on through those, you can go through. I'll go through all this. I should have selected these as take them out of the presentation. But you can see there's quite a lot in there. You don't non-ideal gas.
Is this examinable?
No.
No. I was just a question.
You might want to know if you've got a mass flow, how to get to a volume flow.
Volume flow.
Volume flow, yeah, or something like that. But none of these complicated things. Yeah. So heat transfer, again, I would suggest you go through it, but Thermal insulation on pipes. How long have we got? Oh, we've got a bit of time. I'll go through the bit more slowly. Heat flow through a piece of material is based on Fourier analysis, and it says that heat flow through the material will stay constant through that material, but there will be a corresponding temperature drop. The temperature on the outside of this material will be lower, so T2 will be lower than T1. So that's why you put insulation on. If it's curved, you have to do it in a different way. We take a circular element. Again, this, you should have this. Yes, you looked at it. You had it, didn't you? I'll make sure you've got it, but you just follow it through, and from that you can look at this and you can come up with your temperature profile down the line. So inlet, outlet. Now normally that temperature profile is a function of a number of things, obviously the temperature, but also the specific heat of the material, of the fluid. Right, if you're going to do any work on thermal, there are two parameters we use for thermal. One is the U value, and the K value. They're not the same. Lots of people mix them up. You all right there? I thought you were doing your, what's his name? What's his name? The one that used to do that moonwalk.
Michael Jackson.
Michael Jackson. I thought you were doing an impersonation of Michael Jackson. You're all right. Yeah. You're getting overheated with that hat on. You see that? Oh, you're there. I can see it. Right. So don't mix these two up. What's the units of K? That's the rate at which heat transfers through a material, and that K equals watts. And please don't start going into British thermal units or calorific values. Keep life simple. Watts per meter K, and that's degrees Kelvin, but that's also equal to watts per meter degree C, because the interval's the same. So that's your K value. Be surprised how many people have spent thousands and thousands of pounds doing engineering reports and got these two things mixed up. This is the U value, it's in watts per meter squared K. So what it is, it's the amount of heat in watts coming out from a pipe per unit surface area for every degree of temperature. Now that surface area will be different if it's the steel inside diameter of the pipe, the outside diameter of the pipe, the inside diameter of the coating or external diameter of the coating. You have to be careful. Normally what we do is it's safer to use that where that area is the internal diameter of the pipe, because that's the outside diameter of the product. Okay? So Don't mix those two up. And again, this is a simplified version of your overall heat transfer coefficient, or U value. Another name for this is OHTC.
Overall heat transfer.
Bingo. Right. Yeah, so you've got that. Now, to do that, normally you've got here, that's your boundary condition, boundary layers of your product. But nobody knows what that is. You can't put it into design. So if you bind pipe for a certain U value, you take that out. And so you can work out these for all the different layers, 6 layers. But these are all referenced in this particular formula to the R6, which is the outside diameter of a cylinder of soil. But you could equally do with this, where this, your reference down radius, is your radius, internal radius of the pipe. In other words, half the ID. Okay. And then you've got your profile.
Here's the previous slide, sir. What's the value H stands for? What does it stand for?
It's a film coefficient. It's a non-dimensional coefficient. I'm saying forget it. Just forget that. We don't go there. Right. So if you've got a temperature profile like that, normally normally that curve, temperature curve, is exponential. And I think in this here you should have, I gave you the formula for it. Right, okay. So that's exponential. But just have a quick look what I've got. Yeah. Yeah, okay. You can do it. Right. So, but the inlet, this is in, this is out. Here. The heat going into the piped inlet is the mass flow times the specific heat of the product times its temperature of the product. So that's mass at inlet, specific heat and temperature at inlet. Assuming that stays constant at outlet, then the heat here, so Q in, Q out, so if that's the heat going in inlet to the pipe there, and this is heat in the fluid coming out, where's the other heat gone? This is the heat coming in, and this is the heat in the fluid coming out. Correct. It's gone out radially. So that is a function of that. But if you take this, if you calculate one of the examples, I've calculated this out for you, that, and calculated that, and you can calculate what the total heat loss from here. But what happens sometimes, people assume a temperature that they want, and from that they will work out a heat loss, the U value, and what they do is they then say work out the U value based on the inlet temperature or temperature. What they're doing, or this has gone out, beg your pardon. The heat loss is U value. So the U value times the area times the temperature. Now that area is the total surface area through which the pipe heat lost. But T, it can either be what temperature. You can either put in the inlet temperature, you can put in the outlet temperature. So if you work this on an exponential, is one way, and say, right, halfway along, that's my temperature, and you can put that temperature in here. So this equals this minus this. So if I put that as minus, and this equals U A T. And that T I can use two things. I can work out what it is using an exponential decay halfway along, or I can take the temperature here being a straight line. Whoops. So in the middle. So this one here, the temperature is T1, T in plus T out over 2. And what you find is that if you do that, you'll end up with a higher U value. So this is telling you there's more heat going out of it than there is with the exponential one. Now that doesn't sound significant, but when you come to do it and you're working out the cost, the horrendous price of this stuff, then it's important. If you've got a factor where the U value is, say, instead of 2.5, it's you need a higher one. You can get away with a higher one. The higher the U value, the lower the level of insulation you need. Make sure it's that, you got it the right way around. So the higher the U value, the less thermal insulation. So what tends to happen, they've worked out this, based the U value calculation on this, and said, okay, my temperature here is higher, so I'm losing more heat, so therefore I need more insulation. But if you'd have done it with the exponential one, you would have found out the temperature isn't as high in the middle, so this would have been lower, and therefore your U value could be higher. So you don't need so much insulation. The lower the U value, the more insulation you've got. So make sure you understand all this. If there's anything you don't understand from the thing, you just have to send me an email. You've got a month or more yet, haven't you, before any exams? So we need to make sure we iron everything out to make sure you're all working from the same base. Okay. We've talked about that. I've given you the formulas there. These are all tablets. We'll stop now because I think, let me just thumb onto this. If you can't read these on that, you need to write and tell me, and I will send you enlarged figures of them. So that's your axial force. This is what we've looked at. Cool down. The other thing you need to know, and make sure you do know and inwardly digest, you've heard that expression, joule. What's it equal to in watts per something?
Sorry?
What's it equivalent to?
Time seconds.
Newton meters per second.
Times
Clever lad. Right. Don't, please do not equate that to watts over seconds. You get it all wrong. It's called a watt second. So when you've got, for instance, on this one, your thermal inertia goes in here, and this heat. If you use watts over seconds, you won't get an answer. So you try and put it in on the other part of it, you get H value, which is watts per meter K, and then this inertia, but that's joules. So that's watts second. So this is watts second over meters K, and that's watts per meter K. So you put that in seconds, you'll get an answer out. Otherwise you won't get an answer. The best thing is to do a calculation so you understand it. Follow that because it's just straightforward. You don't need that. We've done that. That's your effect of your wax. Wax on the left, and I don't know what that grunge is on the right. But that's what we have to combat with. That's coming out of a pig trap, that on the left. Thermal insulation, just go through it all. You don't need it. But thermal insulation coatings can range from very cheap, which are no good, to very, very expensive. But the one thing the thermal insulation's got to do, when you put it down in considerable water depths, and the more you compress it, the higher its density gets, the more it conducts heat. But the other thing is the higher the temperature, the softer it gets. So the softer it gets, the more it squashes. So, and then they're all subject to absorbing water. It's an absolute veritable nightmare. So that's why we often do pipe and pipe. And that's why these coatings have to be designed for proving that life they're going to be performing after a lifetime. They're going to be doing what they said they were going to do when what you thought they were doing at the beginning. So really should overperform at the beginning and decay, and then perform what you want to at the end. And all these things are secondary material properties, include the bonding, creep, bulk modulus, you name it, go on. So it's a very exacting involvement. But this gives you this is 10-inch pipe. where the requirement is a U value of 1. If I go for a fairly low grade a fairly high grade rather, U value, K value of 0.07, that's the radial thickness I need, which is about 82 millimeters thick. Don't know where the colours have gone on this, which is 92 litres a metre. If I now go for a more meaningful and achievable coating, then that's the thickness I get. When the U value is 0.12, it's still an exceptionally good quality coating, but it's now 190 millimeters thick and 276 litres a metre. If I go for the lower grade coating, which is, say, I can put in 350 litres of water, then 0.165, but don't forget a lot of the ones are much higher than this, 0.29, 0.35. So that is 320 millimeters thickness and 596 litres a metre. So if you look at that, what is all these coatings are much less dense than water. They'll have a density of about 600 or 700. So what's my biggest problem have I got?
The strength of the coating.
Well, it's a bit more fundamental than that. What did we look at? Did I rub it off? Sorry? Who said what? Did you say buoyancy? Yeah, buoyancy. The damn things float. So there comes a point when you can't put this on. But the other thing is you can't bend it without breaking. I've been on the back of a big reeling vessel when we're reeling on, you can hear it cracking. Bang! We never repair it as we're going on. They'll reel it on, and then they'll only repair it as you're reeling it off. But they'll know exactly where the damage is. When they mark it where it's been the bang. So when it's coming off, they repair it in the hope of praying when it goes off and it goes down, it's never going to be bent to the same extent again. So we hope that's been fine, but there's been some tremendous major commercial law cases by companies, especially down in Brazil. You know, there isn't the materials to do it. People want the performance. They don't want to pay the money for pipe and pipe. Pipe and pipe is about, well, some of these, but pipe and pipe can be about £3,000 per linear metre. So you now take 70-kilometre pipeline at £3,000 a metre. Work it out in money. So pipeline installation. I'll just run your way through this. Don't worry too much about it. Yeah. Pipeline. Well, does anybody come in and do anything on pipeline with you? Does anybody talk to you about lay barges? Dave Bruton will come, I think. Have you had Dave Bruton yet? I think he's after me. Well, I won't cramp his style, but yeah. What you don't do is this clever idea. Well, we needn't take the pipes off the lorry, we'll wash them out on the lorry. So they left them on, they put a very high pressure probe up both pipes, which was great until they come to start the lorry. And they found the whole back of the lorry, all the hydraulic piping was all blasted away, back of the truck was all caved in, all the windows are gone, the cabs are full of water. So it's wasn't a very good idea. That's the Piper Alpha, my old barge. She had the best record for laying 4.7 kilometres a day with 36 inch line coming in at north of Shetland now. That's the CMAC, another vessel I spent a lot of time on. That's the top of the CMAC. This is the Lorelei, which is dynamic position, because all those other barges, those, need anchors. So this one doesn't, it's a dynamically positioned. It's had a few dodgy moments, and that's its biggest sister ship, the Solitaire. And then one of the biggest things of this is you've got to get the pipe out to it. Reeling, well, you can see the lengths that we can get on a reel, 10, 12 inch, typical 14 kilometres, 10 kilometres. The beauty of the reel ship, it's dynamic position, it gets right up close to the platforms, or we position straight on. Now the beauty of this is, like for instance, when you put sleepers down on the seabed to lay it so you initiate a buckle over it, you've got to be very accurate when you're laying the pipe down. If you miss the sleepers, you've got to pull it back up again, lay it on the sleepers and take it really. And as I say, we can get very close to it, platforms. I won't go into all this because that's the straightener, that's the tensioner. They do a lot of damage. J-lay is that. Now this barge, those two cranes, before they put this J-lay on, this was going to be the vessel, the Hermot boulder, here in a boulder. These two cranes can each lift 7,000 tons.
Is it a Saipem?
It is a Saipem now. 7,000 tons. It's only lifted it once, I think. The Hermot's done 2 or 3 big lifts. But so what they've done is put this J-lay ramp on. And Dave Bruton will go through all that with you. At least who doesn't, I'll have to have a word. Deep water, that's the J-lay. Yeah. In sport operations, well, pipe, you get involved in getting trenching, ploughs, putting mattresses on, concrete sleepers over on the top of pipe to protect them. It's an endless business. So, right. We'll knock it on the head there, because you'll have had enough as much as I will now, 4 hours.
Can I quickly ask?
Sure.
You said we ignore film heat transfer coefficient and the distance related to that. Why is that?
Say that again to me slowly.
When you were talking about overall heat transfer coefficient, you
Yeah.
said we ignore that film heat transfer coefficient.
Well, there's no way you'll ever know it, be able to test it.
Because you find out experimentally.
Yeah. So you can never buy it. You buy it. You still you use that in your full analysis, but you can't say to somebody, "Give me this overall heat transfer coefficient," because you'll have to design it without it. Right. So just to show you, this is the formula sheets. They're all on there.
They will be provided for your exam.
Yeah, so if you go into the exam and it's not there, I've done your exam questions, and right across the top it's got a big notice. Formula must be, supplied together, must be supplied with it. So
How many questions are going to
10.
I know they're not going to be 10 from your side.
No, there's 2 on mine.
2 of them.
And I don't know whether you can answer, you've got to answer one or two.
Okay. You could answer few.
Yeah.
If you want to, yeah. I know that. Yeah. Thank you.
All right.
Bye-bye.
Well, good luck.
With respect to fatigue,
Yeah.
I would like to know, is it more prone for liquid pipelines or gas pipelines?
Oh, what a question. Well, it depends on your stress range, and therefore it depends on your temperatures, your weights, pressure pulsations in the line, inertial effects. Liquids tend to have more water sort of pulsation, whereas gas tends to be smoother. Why are you thinking of doing something on the thinner project? Are you?
Yeah.
Pick yourself a nice project then. Yeah. It's difficult. I wouldn't like to say one way that mislead you. If it's a gas line aligned with multi-phase flow, then every time the liquid slugs go through, if it's a gas, you won't get that. With gas, you probably find the pressure.
Moses.
The pressure pulses are not as great with gas. So I'd say the gas is less of a problem. Yeah.
I had the opinion that it was for gas lines more fatigue. I thought.
Wow.
In case of any external interference, a rupture occurs and
that's the consequence though, isn't it? Not the actual fatigue itself.
Yeah, I was of that thought.
Yeah.
You got some?
No, wait.
I'm going to bank.
After that?
Who's going to supervise? Have you got a supervisor?
Yeah, Dr. Fu.
Oh, you'll be fine.
Yeah, Dr. Youngshan.
He's a good chap. Brighter than me.
Wow.
See you, my friend.
That's not mine.
Professor, thank you very much for the lecture.
Well, I'm sorry it's too rushed.
Yeah, but I think it has to do with the structure of the program because many lecturers rush at the end because there is not enough time for it.
And it's apparent that I'm rushing at the end. Yeah.
Sorry?
I'm rushing at the end for that, you know.
Just a little bit, just a little bit. No, not that much. Yeah.
They were clean.
Not that much.
We pay a lot of money.
He's a good lad.
Yeah.
I wouldn't worry too much about it.
It will sell.
You have a self, you know.
He just wants to get a high on that liquid.
But it could also be avoided.
I'm amazed.
By this young man's.
Amazing what you get when you accuse him of doing a Michael Jackson, isn't it?
So this was pretty a lot of stuff. Huh?
Pretty what?
A lot of stuff. The notes. It's a lot.
Yes. Well, I've asked them, do you want me to cut it back? And they said no, because it's got to cover the basics. If you start cutting some fundamental things out, people complain. And they said, well, give me more time. And I can't do that.